let's say you speak to a speaker, okay? The sound wave you speak to a microphone. You speak to a microphone, and then the sound wave produced is being converted into electrical signals, okay? So the microphone is converting the sound wave to electrical wave. Now, when you speak, right, there's a variation of the amplitude and also the pitch. So there's a variation of wave or the variation of vibration being transferred into the microphone. So what the microphone does is that the microphone will change this variation into variation in current. Okay, so the microphone changes vibration into current. So you get the variation of current coming out from the microphone. Then this variation of current, what happened? It will pass to the speaker. Okay, let's say this is the sound wave. When I speak, let's say this is what I get. Like this, irregular vibration. Okay, so this, we get a variation of vibrations. Now, when it transfers into electrical signals, same. This is sound wave. And when you transfer it to electrical signals, it is the same pattern, the same manner. Then this variation in current is being passed to the speaker, and then the speaker will give out the sound. Now, in the middle of the process, if there was no transistor, straight away the microphone is connected to the speaker, then you cannot hear any sound coming out from the speaker. Why? It's because of this electrical signal is too small to be heard. So what is the use of transistor? Transistor is like the bridge. It is the bridge between your microphone and the speaker. Transistor, and then you connect to your speaker here. Can be a headphone, microphone, or a loudspeaker. So what is the function? The main function of transistor is to amplify the current from the microphone, and then it's sent to the speaker, and then you produce a sound that can be heard. So it is the core or the main component used in amplifier. Okay, now all the transistors, usually transistors, they are built in, they are already built in the speaker. Okay, already built in together with the speaker. So transistor is like a circuit, okay, a device and then a circuit that we use it to produce amplified sound or amplified electricity. Okay, let's look at how does it look, the device itself, the device itself. So you might have already know this one, that the diode that we learned in the last lesson, we got the PN junction, right? The P type combined with the N type, you get the diode. And then when you combine them, you get a depletion layer. Okay, so transistor is like this. You take one N type semiconductor. What is N type again? N type is they got extra many electrons, right? So it's like doping. I dope it, I mix it with an atom, I get a lot of free electrons. That's N type. So I get an N type semiconductor, and then I sandwich in between a P type. So this is N type, this is N type, and then I sandwich a P type in the middle. So this is a transistor. Now, a transistor is made of 3 semiconductors. We have this one on top. We call it the collector. Okay, the collector. The collector, in this case, it is the N type. It has a lot of free electrons, and the collector is moderately doped. Moderately doped. Doping the more I dope, meaning that the more I mix with the pentavalent or trivalent atom, the more I get the electrons. So if heavily doped means many electrons. If lightly doped means you have only a few free electrons. Okay, so depending on how you dope it, you can dope it lightly or you can heavily dope it. So the collector is moderately doped. And underneath here, at the bottom, this is the emitter. Emitter means that they are the one that supply the electrons. So we call them emitter. The emitter is heavily doped. So they have a lot of free electrons because they are the one that supply, right? So they have to be heavily doped. So these two, they are the same N-type. The only difference is that one is moderately doped, one is heavily doped. Now in the middle, we have the P-type. P-type has more holes than electrons, right? But the P-type here is very lightly doped, only lightly doped, meaning that it has only a few holes. And not only that, it is also very, very thin. The middle part is very, very thin. This one, the collector and the emitter, is almost the same in terms of the width, but the middle part is very, very thin. The middle part, we call it what? If this is the collector and the bottom is the base, the middle, this is the collector, the bottom is the emitter, and the middle, we call it the base. So we have collector, emitter, base. The base is only lightly doped. Okay, now this is the NPN transistor. So we pronounce it like this, NPN. So we call this NPN transistor. Okay, now a transistor has two depletion layers. Our diode has only one because you join two metal. Now you join three. So you got two depletion layer. One is here, another one is here. The moment you join them, then they'll start to exchange the charges, and then the depletion layer will form, and then there will be junction voltage before you even connect to the circuit. Okay, now on the other hand, I can have another type of transistor. So this one I take a p-type. So a p-type means that it has a lot of holes. P-type I dope with what? I dope with trivalent, right? I dope with trivalent, so I have got a lot of holes. And then sandwich in the middle is the N-type. N-type has more electrons than hole. Okay, now again, this one is moderately doped and we call it the collector. At the bottom, this is emitter and it is heavily doped. Heavily doped means that it has, now because this is p-type, right? So it has many holes. The collector has less hole compared to the emitter. So this is heavily doped and this is moderately doped. How about the middle? The middle, same. The middle, we also dope it lightly dope. Later I'll explain why we want to lightly dope it and why we want to make it so thin. Okay, lightly dope means that it has only a few electrons, maybe 1, 2 electrons. Okay, so for this PNP, the base has few electrons. For the NPN, the base has only a few holes. Okay, focus on the base because the base is the most important at the middle, this layer here. Again, for the NPN transistor, the base has very few holes and it's very thin. And for the PNP, the base, in this case, it has a few electrons, not hole, because it is N-type in the middle. Okay, so this is the basic structure of a transistor. We got two types, PNP and NPN, depending on how you mixed it. Okay, now a transistor got three junctions, three terminal. Let's say I take one example of NPN. NPN. So this is collector, base, and then emitter. Here we got one terminal coming out from the collector. And then here we got one terminal coming out from the base, and another one terminal is from the emitter. I label this C, B, and E. Three terminals, meaning that I can combine two circuits using only one transistor. I can combine my circuit like this. I can combine B and C. I put a resistor here. And then I can combine another one from C to B. I put a resistor here. I got two circuits, right? Three terminals, I can form two circuits. And you can see this circuit, these two circuits, they both share the same base. Because this base branches out into two. So this base is being shared. The terminal that is being shared, we call it the common. So in this case, what is the common? The common is the base. Okay, because the base is being shared by the collector and the emitter. If I connect my circuit like this. Now, I can also connect my circuit like this. Again, NPN. And then I connect the collector to the emitter. So here I join a circuit, put a resistor, and I connect to the emitter. And then I take another circuit from the base, I connect to the emitter, another resistor. So this is a different connection. They are sharing what? They are sharing the emitter. So in this example, the emitter becomes the common. Okay, so this is the base being shared. This is the emitter being shared. So the emitter is common. So there are a few different connections. Now, in all the examples that I will show you later, we will only focus on one type of connection. Which connection do we use? We will focus on this one, the second one, which the common is the emitter. Okay, so in all the examples that I show, the emitter is the one that is being shared by the collector and the base. So we will use the emitter as the common, this one. Okay, now, nomenclature. What is the symbol of a transistor? Okay, you see, here we would, the base is being shared by, sorry, the base is the one at the middle, right? The base is the one at the middle. So we will start our symbol like this. And then like this, we draw two arrows coming out like this. Three terminal, 1, 2, 3. This is the base because it is at the middle. The middle one is always the base. And then which one is the collector? Which one is the emitter? They both look the same. So the way we differentiate between collector and emitter is we look at one should have an arrow. One should have an arrow. The emitter will be the one that has an arrow. Let's say if I draw my arrow like this, this one having the arrow, it is the emitter. That is how we differentiate it. Out of the two, one will have an arrow. This arrow is showing it's like the direction of a current. Okay, so middle is base. The one with the arrow, that is emitter. So left only one, this is the collector. Okay, now after identifying the terminals, how do I know? Is it an NPN or is it a PNP? Because we got two types, right? Is it NPN or is it PNP? Okay, we look at the arrow direction. The arrow shows the current flow, and we know that current always flow from positive to negative, right? Meaning that positive P to negative N. So you follow the arrow. This arrow is pointing here, meaning that it is flowing from positive to negative. So P to N. This is PN, so up here it is N. So this is NPN transistor. Okay, this is how we identify the type of transistor. Again, the terminal, the one with the arrow is emitter, the one at the middle is base. And then we look at the arrow, current always flow from positive to negative. So this is P, this is N, and the other one must be N. So this is a PNP transistor. Now, if I change my drawing like this, let's say we do like this. Like this. Okay, what is this? Label the terminals. Middle, base. The one with the arrow, emitter. So this must be the collector. Is it PNP or NPN? Okay, look at the arrow. Here we have positive to negative. And this N must be negative. Okay, so if P in the middle, that must be NPN. Okay, yeah? So first is you need to know how to identify the type. This will be asked always, even in the SPM objective, everything. Okay, it will always ask you, what is this type? What is this type? Okay, yeah? Now let's try one more, and then we'll go to the next one. Okay, let's say we have like this. Like this. Okay, sometimes you can have a circle. You may have a circle, you may not have a circle. Okay, because sometimes you see the symbol has a circle, right? Now, okay, what is this? The one at the middle, base. Oh, I forgot the arrow, sorry. Okay, let's do this. Let's do this. Okay, the one at the middle, base. The one with the arrow, that is emitter. This is collector. NPN or PNP, okay, it's pointing in this direction. So that means that it's going from positive to negative. So N at the middle, then this must be P. So this is a PN, a PNP transistor. Okay, let's go to the next part. Okay, now next we look at the action of a transistor. How does it work, really, a transistor? Okay, so you see, let's say we have an example of a circuit here. I connect to two circuits. Remember, we got three terminals, right? This is the collector. Here is the base. And let's say this is the emitter. How do I know this is the emitter? Remember just now I said what? The emitter is the common. The emitter is the one that is shared. So you see these two circuits. This wire down here is the one that is being shared by the two circuits. So that must be the emitter. Okay, so here is emitter, up here is collector, this is base. Let's say if I connect to a battery, a power supply. Okay, I connect, say, positive, negative, this is 5 volt, and I connect a resistor, R. The resistor, just to keep the current low, okay, not too large. Now, here I connect to a switch. Here also I connect to another switch. And here I connect to another power supply that has a lower voltage, 0.7 volt. and one more resistor here, R. Two circuits connected to a transistor. Okay, how does the transistor amplify? Now we will look at how does the transistor work by amplifying the current. Okay, here we have two circuits, right? Now I want you to know that these two circuits, one is connected in forward bias, another one is connected in reverse bias. Still remember your forward bias or not? Okay, recap a little bit. What is forward bias? Forward bias means that the positive terminal is connected to the p-type. Negative terminal is connected to n-type. Must be fulfill these two. If one is off, then it's not forward bias. Okay, even though it's like positive to positive, negative to positive, this is also not forward bias. Must be two terminal, same. Okay, look at the circuit that connect the emitter to the base. Let's call this circuit emitter base. Okay, because we have this emitter connect to base, so this circuit will call it emitter base circuit, or I short it as EB circuit. And this circuit, I connect the emitter to the collector, right? So this I would call it emitter collector circuit. So that's EC circuit. Now, the emitter base circuit must be connected in forward bias with the transistor. How do I know forward bias or reverse bias? Okay, what type of transistor is this? Say we are using NPN. Now, in amplifier, we will always use NPN. Always you will see NPN is more usual, more common to be used in amplifier. Okay, but sometimes you will see PNP as well, but NPN is the one more common. Okay, now, so how do I know, is it forward bias or is it reverse bias? Okay, see the terminal. This one is positive, this is negative. See the positive connect to what? Is connected to P-type, the base. And this negative terminal is connected to the emitter, that is N-type. So positive to P, negative to N, that is what? Forward bias. Okay, so this one is forward bias. The emitter base circuit must be forward bias. And the emitter collector circuit, the second circuit here, look at the terminal. This is positive, and then connect to N-type. That is already reverse, right? And this negative is connect to this negative. Okay, this negative to negative is correct, but this positive is connected to, here is N-type. So it is in reverse bias. Okay, so this one, write it down here, reverse bias. Is it always must be like this? The emitter base is forward, the emitter collector is reverse. Is it always must be like this? Answer is yes. Always must be like this. If you don't connect like this, then it doesn't work. Okay, so in all the questions, how they will ask you, they give you a circuit, and then they ask you to check, is this connection correct? So what should you check? You check whether it's forward or reverse bias. Okay, they give you the circuit here, they change the terminal. They say, okay, is this connection correct? So you check, the emitter base must be forward, the emitter collector must be reverse bias. Always, okay? Now that's the first thing, That's the first thing. Okay, now let's see next. This is reverse bias, right? Let's say if I switch off this switch, okay. Here I call this switch 1. Here's switch 1, and here's switch 2. Let's say I open the switch, meaning that no current is flowing. Open switch 1. Okay, so no current is flowing in the emitter base. Can the current flow in the emitter collector circuit? This circuit. Because it is reverse bias, so no current can flow. Remember, reverse bias, current cannot flow. Okay, and plus you got two depletion layer here. This depletion layer is going to prevent the electron from crossing. It will prevent the electron from crossing up here. So there will be no current flowing in the reverse bias circuit if this is switched off. Okay, yeah? So let me write it down here. When switch 1 is turned off, meaning that no current, current cannot flow in the EC circuit. Why? Because it is reverse bias. Okay. How about if I close the switch? If I close switch 1, meaning that the current can start to flow in the base circuit. Okay, let's label. Let's say I close this. What will happen? Let's see. Now I close this circuit. So current starts to flow in this circuit. So current coming out from here, pass through here, and it flows to the P-type, and then come up from the emitter, come back here, come back here. Okay, because the base circuit is forward bias, so what happened when you turn on the current? Forward bias, current can flow, yes. And not only current can flow, this junction voltage, this depletion layer, it will disappear. Because when you turn on current in a forward bias, all the electrons, they will jump. They will jump and they will fill in the holes, and then it will destroy the depletion layer. Then the depletion layer no more. The depletion layer will be demolished. It will disappear. Okay, but of course you have to make sure that the voltage here is larger than, what is that, junction voltage for the current to flow. Yes, must be larger than the junction voltage for the current to flow. So what is the junction voltage? About 0.6, right? 0.6 or 0.3, somewhere around that figure. So if I put a 0.7 here, then current can flow. Okay, when I turn on the base circuit, meaning that current can flow in the base circuit, and then what happened to the electrons here in this emitter region? What happens to the electron? These electron, right, they will start to cross. Okay, now you see this one, they'll cross here, they will jump, they'll jump, they'll jump, they'll jump. Let's say we have 5 electrons jump in. Okay, 5 electrons jump in. What happened to the electron? Now the electron is in the p-type, in the middle. Initially is at the n-type, right? Now they diffuse into the p-type, the base. And what happened to these 5 electrons? Now remember I said the base is lightly doped, meaning that it has a few holes. It only has a few holes. In this case, let's say it has only 3. Out of these 5 electrons, 3 will go into the hole. 3 electrons will fall inside the hole, and when the electron fall inside the hole, they will come out from this circuit here. Come up from the base circuit, and then they go to the positive plate. Okay, that process is recombination, right? We say the electron has recombined with the hole, and then it goes into the circuit. Now, there are 2 left, 5 cross, right? 3 go in. Another 2, where do they go? Another 2 electrons, right? They stay in this middle section, right? And because this middle layer is very, very thin, so the positive charge at this end, they can pull the electron easily. They pull the electron, meaning that they accelerate the electron to the other side. To where? Up here. All the electrons that stays in here that did not get combined with the hole, they get accelerated to this end here, this collector circuit. And they will enter the circuit, they go to the terminal here. Okay, now, meaning that this circuit is, remember, it is in reverse bias, right? It is in reverse bias. How come the electron can cross if it is in reverse bias? Understand that reverse bias does not allow majority charges to flow, but it allows minority. Let me write this down. Reverse bias does not allow majority charges to flow, but it allows minority charges. Okay, what does that mean? Now let's see. This is the, let's say we have a diode. P-type, N-type, P, N. Here we have the electrons, and then we have the O, okay? Now, if I connect it like this, this is positive, this is negative. Is this reverse bias or forward bias? Positive to N, negative to P, that is reverse, right? So reverse means that this electron, they cannot jump. Okay, what is the majority charge on the right hand side here? Electrons are the majority charge. On the left hand side, the holes are the majority charge. So if you connect in reverse bias, this majority charge, they cannot jump. Okay, so what happened to the electrons on the other side here? Here also got electron one. Doesn't mean that electron all are at this side. It's just that the majority is on this side. The electron on the left side, they are the minority. Okay, so electron on this side, they are the minority. So we call it minority charge carrier. The majority is over here, this N-type. The majority cannot cross because this positive is attracting it. But the minority can come because it is attracting it to the right side as well. Okay, so meaning that reverse bias, it is attracting minority charges to cross. That's why I said here, reverse bias does not allow majority charges, but it allows minority charges. And also the same reason, the electron that diffuse in the p-type, they will be accelerated to the positive plate up here in the collector circuit. Then you get a complete flow of charge in the collector circuit. Okay, now, okay, so what is the bottom line? The bottom line is when I switch on my base circuit, only then the electron can cross here in the collector circuit. If I do not switch on my base circuit, then no electron can cross because it has got two depletion layer. The moment I switch on the base, one depletion layer is demolished, and then the electron can cross, and then they can complete the circuit. So we can say that the base circuit is controlling the collector circuit. Okay, base circuit is controlling the collector circuit. Now let me do a table like this. You see, let's say this current over here, I call it IC, the collector current, and the current over here is IB. This is the base current. Sorry, the direction wrong already. This one, the current is flowing in. in this direction, right? IC. The electron is flowing up and the current is flowing down. They are opposite direction. Okay, we do like this. Switch 1, switch 2, and then we have IB and IC. When switch 1 is closed, switch 2 is closed, is there any current flowing in the base IB? No. No current. And this one also, no current. If I open switch 1, if I put a tick, meaning that I close the switch, I close the circuit. Okay, circuit closed. So there's current flowing in switch 1. And switch 2 is closed. Is there current flowing in the base? Yes, right? Current will flow in the base because this switch 1 is a closed circuit. So yes. And the collector current, no. Okay, because switch 2 is open. Now, I switch off switch 1, and then switch 2, I open it. So there's current flowing in the collector circuit. Is it? Is it true? If I switch off switch 1, you see clearly. Switch 1 is off. Switch 2 is on, meaning that I switch, this is on, but this is off. Is there current flowing here? Answer is no. Again, because it is in reverse bias. Switch 1 is off, no IB, and this also no current, even though the switch 2 is on, because it is in reverse bias. Okay, now last one. I switch on, there's current flow, and there's current flow. Look at the IC. The current flowing in the collector circuit. No current, no current, no current. Yes, this one got current. So there's only current flow when the switch 1 is turned on. We can say that the current in the IC is controlled by the current in the IB. So let me write it down here. Current in the collector circuit is controlled by current in the base circuit. Okay. So this become a very important characteristic because I can control the current in the base. If I use a variable resistor, I can increase and decrease the resistance, and I can control the amount of current in the base, thus controlling the current in the collector circuit. Okay, now one more thing. You see, here, if I turn on, okay, I want to clear this first. I don't have space. If you want to take a snap, you can take it now. I want to clear up this space. So what we have known so far we already understand that the current in the collector is controlled by current in the base. If the base is not switched on, then no current is flowing, even though this is closed. Now, next one, you see. Let me clear this. Okay. Remember I said the electron that crosses here, the electron that jumps into the p-type, some of the electron will flow out. and some of the electron will cross, right? Now, the number of electron that crosses and flows to the collector is always bigger than the number of electron that flow out. This is your transistor, N, P, N. Here, when you turn on the two circuits, let's say we have 100 electron come in. 100 electron diffuse into the p-type. Because the p-type is only lightly doped, right? So it contains only a few holes. Let's say only one. Only one, meaning that only one electron can recombine and it flows back into the circuit. What happened to the rest? The rest 99, the 99 can cross and they complete the circuit. So you always get more electron crosses and less electron that goes to the base. As a result, the current that flows out from the collector is always bigger than the current that flows in the base. So you can see here 99 electron is coming out. This is only one electron. So I can say that the IC is 99 times bigger than the IB. Okay, 99 times bigger than the IB. Let's say if I double it, I turn on, increase the current. So we have 200 electron diffusing into the p-type. So out of 200, okay, maybe 2 go out because it has only less hole, right? Very few holes. So only 2 out. And what happened? 198 can cross. Okay, again, you can see when I double the current, 200 electron, this IC also double. From 99 goes to 198. It also double. So what does this tell us? When I double the current coming out from the IC is also double. So if I triple it, then the IC is also triple. Meaning that when current in the base circuit fluctuate, when the current in the base circuit changes, the current in the collector also changes. And the current in the collector changes in the same manner as the current in the base. And it remains 99 times bigger than the current in the base. Okay, we can say that the current in the wire, in the IC, okay, the current come out from the collector is the amplified version of the current in the base circuit. It always maintains 99 times bigger, no matter how you change this. Because you double it, it becomes double. You triple it, it triples. Always it maintains 99 times. So if you have a variation of current in the base circuit, let's say your current looks like this. Okay, this is the current graph. This is the IB. How does the IC looks? The IC will have the same pattern, but much larger current. The green one, this is the IC. Higher up, so the magnitude is bigger. Pattern is the same. So we say that the variation of current is the same as this variation of current. The pattern is the same. The manner is the same. Just that it is being amplified. That is the function or the working of a transistor. Okay, by allowing more charges to flow through and less charge to flow in the base. It is because of the design of the p-type is very thin and it is likely do. Okay, so if you connect the base circuit to your microphone, okay, you speak to the microphone, so there's a variation of current. Okay, the microphone changes the voice into variation of current. And this variation of current, inside there's a transistor, and the output current, output that's connected to the IC, the collector, has the same variation, but amplified. So you hear your same voice because it has the same pattern, same voice, but much louder at the speaker. Okay, so whenever we make a small change in the current, there's a large change in the output current. Whenever we make a small change in the input current, there's a large change in the output current. How large? The change we make is usually in microampere. This is the IB. We change only microampere, like 1 microampere or 2 microampere. That will result in the change of milliampere for the IC. Milli is much larger than micro. Milli is what? Milli is -3. Micro is -6. So that is like 1,000 times larger. Okay, 1 milliampere is 1,000 times larger than microampere. So you do a little bit of increase in microampere, that will get a change in milliampere in the IC. Okay, so that is the core structure, the basic function of an amplifier. Okay, amplifier. Now, where do you connect? Where do you connect your speaker, and where do you connect your microphone? Where do you connect your speaker? Where do you connect a microphone? Where is the input voltage? The input is the base, right? So you connect your microphone over here. On the left, connect your microphone here. And your speaker must be at the output, meaning that the collector, it can be here, or it can be here, or it can be anywhere, as long as it is in the collector circuit. That is the output circuit. Output circuit is the collector. The collector has the amplified. The base is not the output, that is the input. Okay, take this down and I will erase this and I'll go to the next one. Okay, we continue. Suppose that we have let's take one example. We have a transistor here. Okay, what type of transistor is this? This is the base, the one with the arrow, emitter. This is the collector. Look at the arrow. This is like the current flowing from positive to negative. So PN, NPN. So NPN and then emitter here. Now, let's say if I say the current IB, and let's compare the current IB and IC. We know that IC is always larger, right? It's always larger than the IB. So if this is 0, then this is 0. If I increase to 0.1, and this becomes 2. Increase to 0.2, I get 4, and I increase to 0.3, I get 6. They are all in ampere. Ampere, ampere. Now, if I want to calculate what is the amplification of this particular transistor, how do I calculate it? I can take IC divided by IB. If I take the ratio of IC and IB, then I get what we call the amplification factor. And please take note, this is very important. Amplification factor. It is the ratio of IC and 2IB. So if I take 2 divided by 0.1, that's 20. I take 4 divided by 0.2, I get 20 also, meaning that this transistor, the amplification factor is 20 times. 20 times. Okay, 0.1 you times 20, you get 2. You times 20, you get 4. All the current in the IC is 20 times larger than the current in the IB. No matter how you change it, it remains as 20 times. So this 20 is the amplification factor. Now, we see that all of this times 20 becomes 6. So this amplification is a constant, right? It's a constant. It does not change. It remains 20 times larger. So meaning that IC divided by IB is a constant value. In this case, is 20 times. Always 20 times. If I plot the graph, of IC against IB, what do I get? A graph of IC against IB, I will get a straight line. Starting from 0, a straight line. Why a straight line? Because IC divided by IB is constant, meaning that the gradient IC divided by IB is a constant gradient. It's a straight line. Okay? And IB is normally plotted in microampere. IC is normally plotted in milliampere. Okay, always you will see the graph. This will be in milliampere, this will be in microampere. Why? Because the amplification is around a factor of milli and micro. If you plot ampere here, then you'll see very large number, too many zeros here, very large number on the y-axis, because it is like out of range. So we plot milli. Okay, we plot milli. Now, this is microampere, this is milliampere. What is the amplification? The amplification is 20 times. Doesn't mean that if this is micro, this is milli, the amplification factor is 1,000 times. No. The amplification factor is the gradient, okay? It's the gradient. So it is 20 times. So meaning that if you take the gradient of this, okay, like this, the IC is IB, you take the gradient y divided by x, okay, you get 20 times for this one, right? Okay. So let me give you one example. I give you one example. Sometimes they'll ask you to calculate. Okay, they give you a graph, and then they say, okay, what is the amplification factor? This is 0.3, and this is 2. Okay, then we take M gradient equals to IC over IB. We take the gradient, that's 0.3. Don't forget the unit. This is what? Milliampere. You have to change it. Times 10 milli times 10 minus 3 divided by, and then this 2 times micro, so 10 minus 6. Divide this 2. Okay, we get around 150. So that's 150, no unit. Okay, no unit. So it's 150 amplification factor. So meaning that the current in the collector circuit output is 150 times larger than the current in the input. One line shows one transistor. This is one transistor. If I plot another line, this is another transistor. Transistor X. And this is transistor Y. Okay, I put one more. This is another transistor. Transistor Z. Because one transistor can only have one amplification factor. So there has to be one line. This is one line, one line, one line. Which one has the highest amplification factor? Compare. The green one. Why? Because it has the largest gradient. Largest gradient, largest amplification factor. So transistor X has the largest amplification factor. Okay, now, any question? If there's a question, let me know in the chat. Okay, so we have discussed so far the working of a transistor and the grafting and everything, all this nomenclature things. Now we look at the circuit itself. The circuit of the amplifier, the amplification circuit. Okay, here I will draw my transistor like this, in this symbol. And then I will connect. I will connect to a battery. Let's say this is how a normal circuit, like a common, the usual circuit would look. Okay. This 5 volt plus minus R. We have one switch here. We have another switch here, right? And then here we have a battery. And then we put a rheostat. And then here I have, okay, that's it. Now, first we look at the type of the transistor. Again, we will use, now this one is a common, right? This line is being shared by two circuits. So this must be the emitter. This is the emitter. That is the base. This is the collector. PN. So this is NPN. Why we use NPN? Not PNP. Because NP doesn't mean that you cannot use PNP. You can use PNP, but normally in amplifying circuit, we use NPN because electron is more easier. They flow easily compared to holes. That's why we use N-type. Okay, we said that the electron, they have higher mobility. They flow better compared to holes. That's why NPN is more common. And usually in the amplifier circuit, you will see NPN. Okay, so we mentioned that changing the base current can change the collector current, right? So if I put a rheostat here, what is the function of a rheostat? Rheostat can change the resistance, right? If I drop the resistance, then the current will increase. If I increase the resistance, then the current will become very small. Okay? So by adjusting the current in the base, I can adjust the current in the collector. So you can think of the base like a gate. This is like a gate. When there's current flowing in the base, it opens the gate for the current flowing in the collector circuit. No current, then the collector circuit cannot flow. How do I form my amplifier? Okay, I put my loudspeaker here. I put it here. This is my loudspeaker at the collector circuit over here. Where is my microphone? Now the loudspeaker must be on the collector circuit, right? Where is my microphone? My microphone. Now for this one, right, there are two power supply. This is 5 volt and this is 0.7 volt. Normally this one is smaller. This one is very small voltage and this one is large voltage. Here, I would replace this with a microphone. Okay, so microphone is now my input voltage. Like this. Okay, my input voltage. And then also sometimes you will see I will also put one battery here. What is the function of this battery? This battery is to make sure that the input voltage is not smaller than the junction voltage. Remember I said, for this current to flow in the forward bias, it has to be larger than the junction voltage, right? So sometimes they put a battery here, 0.7 volt, just to make sure that the current in the base circuit is always larger than the junction voltage. Because without the battery, if only the microphone, sometimes if you don't speak, then the voltage becomes too small. Okay, so it will drop below the junction voltage. Right? So sometimes they have a rheostat here, sometimes they do not have a rheostat. So if you have a microphone, then I don't need to put the rheostat. Because microphone is the one that adjusts the current. Okay, is the one that adjusts the current. So what will I put? I will put a capacitor. Capacitor. What is the function of the capacitor? The capacitor, it will block the current flowing. You see, now, the current from this circuit on the right. Current flowing out from here, positive, here, and then it enters the collector, right? Enters the collector, and sometimes the current can flow over here. It can flow in the microphone, it can flow to the microphone. We don't want that to happen. Okay, if current flow in the microphone is supposed to be the input. So there should be no current flowing to the microphone. So the function of the capacitor is to block the current. Because capacitor, it does not allow the DC current to flow through. It only allows AC current. Only allow AC current. So that's why we put a capacitor there. So if the question asks you, why is the capacitor there? What is the function of the capacitor? Is to prevent the current from flowing to the microphone. Okay, so the current, it will stay here. Okay, so that is one example of the amplifying circuit. There's another one example, which we will look at it after we take our 2-minute breaks. Okay, now I give you 2-minute breaks, 3-minute breaks, and we will continue at 11:15. 11:15. Okay, let's continue. Let's continue. Okay, I'll discuss 3 circuits with you, and that will end the class. 3 circuits you need to know. Okay, so first is, of course, the amplifier, the amplifying circuit. This is the more common one, okay, which we use potential divider. Okay, so if you look at, okay, here got one capacitor, here got a capacitor. Now this part, you see this first, this circuit looks complicated, right? It looks complicated because here they join here, and all this. But this part is actually the potential divider. What is a potential divider? If you have a like 12 volt, you have 2 resistance, 12 volt, and this is 2 ohm, this is 4 ohm. How do you know the voltage over here? V. This is like a potential divider circuit, okay? Meaning that the 2 volt, the 2 ohm and the 4 ohm, they share the voltage. How do I calculate the voltage here? I take 4 over the total resistance, 6. Okay, meaning that 4 plus 2. And then I times 12. I get 4 over 6 times 12. I get 8 volt, right? So meaning that here is 8 volt. This one, if this is 8 volt, then this one is 4 volt. So this is potential divider, meaning that the 2 resistors, they each share a certain portion of the voltage. Notice that the larger resistor will have more voltage, right? The smaller one, the lower resistors will have the smaller voltage. So the larger one, the high resistance, they will get more share of the voltage. Yeah, we can calculate using this formula here. This one. This is the potential divider formula. Now we are not going to talk more about the potential divider. That is you have another lesson for that one, right? Okay, so the point I'm trying to make is this 2 resistor is the potential divider. This is about 50 kilo ohm, and this is 5 kilo ohm, much smaller. Okay, now meaning that here it will have a potential difference. If I say that the battery has a 12 volt, then meaning that the potential difference between these 2 points A, B is 12 volt, and the potential difference between here and here is also 12 volt, parallel, left and right, same. Okay, so the 50 kilo ohm will share some portion of this 12 volt, and the 5 kilo ohm also it will share certain portion of the 12 volt. Okay, that is the function of these 2 resistors. So if this is 5 kilo ohm, then it will have a certain voltage over here, right? The higher the voltage, if the 5 kilo ohm, if this resistor get higher share, then the current will increase in the base circuit. Let's say you switch resistor, the 50 is over here. It gets more share of the voltage, the potential difference become larger, and then the current will be greater in the base circuit. If the current in the base circuit become greater, it increases, then the current in the collector will also increase. Okay, so this is one typical connection of the amplifier. Again, this capacitor is to block the current flow, the current flow from the power source here coming out. It flow here, it can go here, down here, and it enters here, it cannot pass. Okay, it cannot pass. So it is to block this current from the flowing to the microphone. So this is the first circuit. And one thing, the microphone, what is the function of the microphone? It transform the vibration of sound to what? To electrical energy, right? And then what is the function of the speaker here? The speaker does not amplify. This is a lot of confusion. The speaker, a lot of people, they think that the speaker is the one that amplifies the sound. No, the speaker only convert the electrical signal or the voltage to the sound source, the sound vibration, back to the source. Back to the voice. That is the function of the speaker. Only connect the electricity back to sound. It does not amplify. Who is amplifying? The circuit. This circuit is the amplifier. Okay, that is the function of the microphone and the function of the speaker. Okay, so again, the potential divider is the one that provides the voltage over here and over here. Okay, and you have a variation of voltage from the microphone. Notice that this circuit is different from the previous one. The previous one has a battery, right? At the base circuit. This one does not have a battery. The voltage is provided by the potential divider. So it does not need a battery. Okay, next circuit. The other two, and then you can take a rest. Transistor as an automatic switch. This one is also very important. Now, automatic switch. First, we have light operating. Switch. Automatic light. Okay. Now, we will arrange our circuit like this. Here we put a resistor. Here we put a LDR. And here is the power supply. Let's say 12 volt. And we put a light bulb here. Okay, again, this transistor is NPN. That is the emitter, collector. This is the base. I put another resistor here. Okay, what is the function of the LDR? First, we look at the LDR. The LDR is a variable resistor, meaning that its resistance can change depending on how much light is shining on it. If the light is high, the intensity of the light is high, then the R is very low. About a few hundreds. It can drop to a few hundreds ohm. If the light intensity is very low, that means in a dark room, then the resistance become very high. That can reach about 1 mega ohm, like 1 million. Mega is million, 1 million ohm. So this is the function of the LDR. Depending on how much light is shining on it, this resistance will change. Now, let's see how it works. You see, here is 12 volt, meaning that here to here, the potential difference is also 12 volt. In the night, during the night, no light. So what happened to the resistance of the LDR? During the night, the resistance of the LDR increases, right, to 1 mega ohm. So when this increases to 1 mega ohm, then it will take greater share of the voltage, because this is a potential divider, right? The LDR and the 10 kilo ohm resistor, they are both sharing the voltage 12. When the resistance of the LDR increase, then the voltage across the base circuit will also increase. Okay, because this high resistance, it will have high voltage across here. If the resistance decrease, then the voltage also decrease. So the voltage is controlled by the resistance. Okay, so what happened during the night when the LDR resistance is very high, then the voltage across it is also very high, and the voltage across this one is become very low. They are sharing the voltage. Remember, they are sharing. When this become high, then this will drop. So if this become high, then it will have enough voltage to cause current flow in the base circuit. Okay, you can see this base circuit here. The LDR is connected in the base circuit. This circuit. Here, here, here. So it will cause current to flow in the base circuit, and thus it will open the gate for the current to flow in the collector circuit, and thus the bulb will light up. The bulb will light up, and the bulb will light up with an amplified current, because this transistor amplifies the current. Not only it amplifies, the transistor can also be used as automatic switch. So this is an automatic switch. Why? Because I don't need to switch on and I don't need to switch off. When the night comes, the resistance increase, and then automatically it flows in the base and it switch on the bulb. It switch on the street lights. Okay, it switch on the night lights. They are all automatic switch. Okay, that is light operating switch. Okay, yeah, you can take a snap for this one, and we go to the last type of circuit. What is the function of this? This 1 kilo ohm. This 1 kilo ohm is to prevent too large current flowing into the base, because we don't want too large current flowing into the base. The base usually it takes small currents, right? So this resistance I put here is to prevent large current flow into the base of the transistor. Otherwise, it will burn the transistor. If too large current flowing here, it will burn the transistor. Okay, so this is the connection of automatic switch. Sometimes they'll ask you, especially in the essay, if you sit for SPM, the essay, they will ask, design a light operating switch, a circuit. Then you have to draw this. Okay, all this component. Now, okay, go to the next one, the last one. The last one, just now is light operating, right? So here we look at heat operating switch. For light operating, we use LDR. For heat operating, we use a thermistor. Okay, what is a thermistor? Same circuit, it's the same connection. Nothing has changed. Just that this, instead of bulb, maybe I put a fire alarm. Fire alarm. Here, same, I got the resistor, 1 kilo ohm. Here, same. Okay, I put the resistor over here. And then here I put this is the thermistor. Please remember the symbol. Okay, like this. This is 10 kilo ohm. Okay, now again, thermistor. Again, the resistance is a variable resistor. The resistance will change depending on temperature. If the temperature is high, resistance is low. If the temperature is low, then the resistance is high. Okay, how does it work? How does the circuit work? Now, when there's fire, temperature increases. When the temperature increases, what happens to the resistance of the thermistor? Drops. When the resistance drops, then the voltage between the thermistor, the voltage across the thermistor will also drop, right? And this will cause the voltage across this base circuit to rise. Because remember, here is 12 volt. The potential difference across these 2 points is also 12 volts. So if the thermistor voltage drops, then the voltage at the base gets the greater share. They are sharing the voltage. Okay, if the voltage across the thermistor increases, then the voltage at the base will drop. Okay, it goes like this, hand in hand. Okay, so when there's fire, temperature rises, resistance drops, and the voltage across the base will increase, and again it will start the transistor. Then current can flow in the collector circuit. Without enough voltage in the base, current will not flow in the collector. Remember earlier, when the switch 1 is open, there's no current flow. No current can flow, right? When I close the switch, then current can flow. This is the same principle, just that we don't have a switch, but we have a potential difference. When the potential difference is very low, means no current flowing, then it's like not turning on. Current cannot flow. So when the potential difference increases, then current can flow. Okay, this part is again the potential divider. Okay, sometimes they'll ask you to calculate. They give you the voltage here, and then they ask you to calculate, okay, what is the voltage here? What is this V? What is this V? So you have to look back at your potential divider notes. Okay, how do I find the voltage? This is V. This is R1, R2. Still remember, right? If I want to find this, V2. V2 equals to R2 over R1 plus R2. And then we times by the total voltage. Okay, we use this formula. Yeah, sometimes they will ask you, they give you voltage here, they give you voltage here, and the resistors. They ask you to calculate what is the potential difference across here, what is here.